Okay, so the first example is of a seesaw where in a park you have a seesaw of a length L. A child is sitting at one end and the father, who's heavier, is sitting at some other position. This is the distance to the child from the center, the distance to the father from the center, and we're given that the plank is uniform of mass 20 kilograms. So that's 20 kilograms. The length is 6 meters from here to here. The total length is 6. The child is 30 kilograms sitting at 2.5 meters, so DC is 2.5 meters, and the father is 60 kilograms. The question is, how far should the father sit from the center so that the thing remains in equilibrium and does not tip over on one side? So the first step in solving this problem, or all problems of this kind, is to make a free body diagram, which means indicate or show all the forces that are acting on the object. Let me explain that. Show all forces acting on, that's very important, on the plank. There are forces that are acted upon by the plank which are not included. So the forces that are here would be the weight of the father is pushing down on the plank, so there's going to be a force here which is going to be mass of the father times G. There will be a normal force here from the plank pushing the father up. This is not to be included because this is a force acted by the plank on the father. So it's not a force on the plank. The force on the plank is due to the father. And then we have a force due to the child, which would be somewhat smaller. So it's going to be mass of the child times G. That's the force here. And then the plank has, the weight of the plank would be also acting here. That's the mass of the plank, which is MP times G. And there will be a normal force here acted upon by the support pushing the plank upwards. So these are all the forces that we can see, and so that's our free body diagram. Now the next step is step 2. We write the equations, the conditions of equilibrium, equations for equilibrium. So the first equation is sum of forces in the x direction is 0. And as we see here, there's no force in the x direction. They're all in the y direction. Okay, that's our x, that's our y. So there's nothing. 0 equals 0. Doesn't give us anything. The next equation is sum of forces in the y direction is 0. So we need to add up all the y direction forces. So we have this one, which is a negative force. So we'll write minus mfg. Then we have the normal force pushing upwards, so it's plus normal. Then we have minus mass of the plank G, and then we have the weight of the child, minus mcg, which is the weight of the child, and they all add up to 0. Now we know the mass of the father, G, plank, mass of the plank, and the child. So from here, when you plug in the numbers, we can get the normal force, which comes out to 1078 newtons. Okay, you can do that by plugging in these values. So now, well, we got the normal force, but we still don't know if it's in equilibrium, so we apply the third condition, which is the torque equals 0. Now, before we apply the torque, we have to decide where to find the torque. Where is the axis of rotation? And in this case, it's evident that it's going to be here. But we could take the axis anywhere we like, and we're going to do that also. We're going to take the axis at some other point. So first we'll take it here. And the reason why we take it here is because there are two forces that are passing through here, and the torque due to these will become 0, and so it becomes easier to solve it if you take the torque at a point where the largest number of forces are passing. So we call this point A, and we find the torque at the point A, and normally it's best to select A so that or where so that largest number of forces are passing through it. That makes the solution somewhat easier if you have more forces passing through that point. So we select this as point A, and now we apply the sum of the torques. Okay, guess we need to make the diagram a little bit again, just to, because it's going too far up. We have a normal force here. We have a mass of the plank G, mass of the child G, and mass of the father G, and this distance is dF, and this distance is dC. So now the torques about A are going to be the torque due to all the forces. And we know the torque is R cross F, which is RF sine theta, and theta is the angle between R and F. So the force is in the y direction and the distance is in the x direction, and that's the same for all of them. So in all cases, in this particular example, theta is 90 degrees for all the torques, and so we can, sine theta is 90, so it's going to be 1, so it's just RF, which makes it much easier. So the sum of the torques is the torque due to this force times this distance. Okay, that's the axis. All distances are measured from the axis. So this is the distance, d father, times m father g. Okay, this becomes the torque due to the father. The next torque is due to the normal force. The distance between the axis and the normal force is 0, so it gives 0 torque. Then we look at this MP, and it's also acting right at the axis, so it's 0 times mpg. This gives a 0 torque, and this is the last one. It's mcg is the force, and the distance is dc, and they should all add up to 0. Now we need to consider the signs. So anything that's clockwise is negative, and anything that's counterclockwise is positive. So the torques, the momentums, angular momentum, angles, omegas, accelerations, they all follow this convention. Now this force is pushing downwards, so that's the fulcrum here, and this force is pushing down. It's going to try to cause it to go like that. So this force is going to cause it to go this way, which is counterclockwise. So this torque is positive, which is written here, which is positive. You can add a plus over here if you like. These two are 0. This force, that's the fulcrum here, and we apply this force here. The child is going to push it downwards. So that's a clockwise torque because it's trying to turn the thing clockwise, and clockwise is negative. So we have a minus sign. Well, now we know the mass of the child, the g, the distance to the child. These are zeros. We know everything except df. We plug in the numbers, and df comes out to 1.25 meters. So the child is at 2.5 meters and the father is at 1.25 meters, which is was an easy result because the father is twice as heavy as the child, so he should sit twice as close as the child. Now, we did this taking the axis at A. We'll now repeat the same calculation by taking the axis over here, which we'll call the point B. Now, evidently, it's not going to spin about here, but just to show that you can take the axis A wherever you like, you can take it over here in space or here, and you will still get the same answer if you do it properly. So we'll do it again with axis over here. Okay, so now we have this plank centered here, normal force here, mass of the plank G, mass of the child G, this is 1.25 dc, and the father is somewhere here which we do not know, that's df, and this is m father G. This is our axis, point B, and therefore, and the axis is vertical because it's going to now supposedly spin like that. So now we're going to measure everything from the axis. Okay, so the sum of the forces in the x is still 0, the sum of forces in the y is 0, and that will again give the normal force as 1078 newtons, because there's no difference in this case, the axis doesn't matter. And now we find the torques about the axis B. So the first force is this one, and the distance is now this, which we call from here, this is x father. So it's going to be x father mfg. Okay, this is our r cross f, which is rf sine theta, which is simply rf, because thetas are still 90 degrees. So it's going to be xf times mg, and this, if the fulcrum is here and the father is pushing down from here, it's going to be a clockwise torque. That's a negative. Now the normal force is going to try to, the normal force will try to push it upwards. That's the fulcrum, it's going to try to push it upwards. And so it's a clockwise torque. And this distance is 3 meters, or let's write it as L by 2 times the normal force. The mg, the weight of the object, is going to try to make it go clockwise, so it's going to be minus L by 2 m plank g, that's this force, and the child is also going to try to make it go clockwise, so it's also negative. And this distance is going to be, well, it's going to be 3 plus 1.25. It's going to be L by 2 plus d child m child g equals 0. Okay, so it's important to have the correct signs. Everything that's clockwise will be negative, and everything is seen based on, all distances are from that axis. Now we have, we don't know xf, but we have the mass of the father, the g, we know the L by 2, it's going to be 3 meters. We know the normal force, which we have here. We have the L by 2 mass of the plank, g, L by 2 is 3, dc is 1.25. All of these are known, and we can solve this to get xf comes out to be 1.75 meters. So this distance from here to here is 1.75 meters. And therefore the distance dc is going to be the L by 2 minus 1.75, 3 minus 1.75 equals 1.25 meters, which is the same as what we got before. So selecting the axis anywhere else would not make a difference. You can select the axis here if you like, but there's no advantage in it. The advantage is a position for the axis is where the largest number of forces, or where the unknown forces are passing through, and then it becomes much easier to solve these problems.